Welcome back, everybody. Today we're going to be looking at 15.8, asking a question that we've asked before, how using different coordinates can help us compute integrals. But in our case, we're going to think about triple integrals. Right, in double integrals, we've thought about how to give different sets of coordinates to the plane to help us out. Here we're going to think about different ways, and this is the first of two ways that we can naturally give coordinates to 3-space to help us with triple integrals. And something that's interesting is that I claim we've actually already done this. We've already done this. In particular, remember the example that we did as our very first example, 15.7 of triple integrals, right? We were computing this triple integral of our humble function x over our Christmas ham, right? And the idea here in terms of setting up our limits of integration was let's move x first because then we get nice consistent start-stop instructions. We're always starting at the paraboloid and popping out at the plane, always starting at the paraboloid, stopping at the plane. Right? And so we said, well, hey, let's move x first. And then we asked the question, well, what's the shadow of this Christmas ham, right? The x shadow. And projecting this back onto the xy plane, we saw that we actually got a circle, right? Or a disk, rather, since it's all filled in for the shadow. There it is. There's our shadow R. And we said, hey, since this is a nice disk, well, let's use polar to describe the YZ plane, right? And so basically, in summary here, we used one rectangular coordinate. So we used the rectangular coordinate x to start, and then afterwards we used polar, right? And then we used polar coordinates. Oops, that's a no. Right, r and theta to then describe the YZ plane. And right here, and this is the idea of what is called cylindrical coordinates. In a nutshell, cylindrical coordinates are where you choose one coordinate to be just your standard everyday rectangular coordinate. And this could be x, like we had up here with our Christmas ham, or it could be y, or it could be z. You just choose one to treat as its normal self, rectangular, and then we use polar for the other two. And this is what we call cylindrical coordinates. And so just as a real quick kind of example to get familiar with what we're talking about here is that this is a way to kind of give an address to every point in 3-space. And so, for example, for this particular point here, I guess first of all we have to kind of choose what coordinate we're going to do rectangular. And for this particular picture here, I'm thinking of z is our rectangular coordinate here. And so if this point, thinking about getting its cylindrical address, its cylindrical coordinates, if in the xy plane, right, we need to swing over 2 pi over 3 radians from the positive x-axis, and then march out in that direction 2 units, and then go vertically, right, in the z direction 1 unit, well then the cylindrical coordinates for our point here in terms of, I'm not sure if there's a standard order here, r, theta, and z. Right, our r is that 2, our theta was the 2 pi over 3, and z is 1. And so this is a way of giving an address to each point in 3 space, right, where we just keep one coordinate rectangular and the other 2 we use polar for. I think a natural question is why is this called cylindrical? And to see why that might be a natural choice, let's think about the solution set that we get to the equation r equals 2. And notice, right, so the solution set is going to be all the points in 3 space whose r coordinate is 2. And so actually, in particular, it does include this point that we were looking at just a moment ago, because its r is 2. But now, if r is 2, well then theta can be, whatever it wants to be. That's not specified. And so we can imagine actually swinging around, right, just kind of swinging this stick all the way around, letting theta be whatever. We'll get kind of this kind of circular halo above the xy plane, right? All of these points have their r equal to 2. But also, right, this equation doesn't care what z is. Z could be 1, like it is for these points, or it could be a half, it could be 0, it could be -5, right? We can take this halo and we can stretch it vertically up and down. And notice as we do that, what sort of shape are we getting? Right, well, we're getting a cylinder. And it's for that reason that cylinders are cleanly defined here. Just by setting r equal to something, right, we get a cylinder. That's where this name comes from. And so with that basic introduction to this essentially new terminology for cylindrical coordinates, let's dive in and let's look at a particular example and just work through it. All right, so we're going to set up and evaluate. We'll go through the whole 9 yards here in the video. The triple integral, which computes the volume of the solid enclosed by the cone, z equals root x squared plus y squared, and the sphere with that equation. All right. And so, if you haven't had a chance to work through this yet, pause the video, see if you can figure out the integral we're going to be working with, see if you can get all the limits of integration, and see if you can then go through and actually evaluate triple integral and find the volume of this solid. All right, well, let's start talking through this one. First off, the integral that we're actually going to be looking at, you might have noticed, hey, like we don't have like a function f of x, y, z that we're told to integrate. Well, not directly, but indirectly we do, right? Because we're told to compute the volume of this solid. And if we want to use a triple integral to help us do that, our function needs to be the constant function 1. All right, so here is the triple integral that we're going to be computing. We have our function, we just need our limits of integration for us to start cranking through this. And as always, we want to draw a picture. And so here we just have these 2 surfaces that are going on. And so we have this sphere centered at the origin. There it is. And pop quiz, what is the radius of this sphere? It is √2, right? Over here on the right, this is the radius squared. And so this sphere is going out to √2, which is like 1.4-ish for its radius. So that's where it's going to connect up with the y-axis and x-axis over here at √2, and I guess here at the top z, it's going to hit √2 there. All right, so there's our sphere, and we also have this cone. This is just going to be just an ice cream cone shooting up in the positive z direction, right? Since square root always spits us out 0 or positive stuff. And so we have this ice cream cone like that. And notice where these things, they're going to intersect. And it's this kind of ice cream coney region with kind of this waffle cone bottom side and this rounded ice cream top right there. Right? And this three-dimensional solid here, that is our B that we are looking at. Right? And so, I don't know, maybe, I don't want to shade it in, and it's going to get pretty busy if I do that. Okay, and so maybe just real quick, let's get a GeoGebra visual on this, get a little bit more perspective. All right, here's our sphere. And notice it is indeed, right, not going out to 2, it's going out to 1.4-ish, √2 for its radius. And if we toss in the cone, right, again, we see it intersecting with our sphere, and it's going to be this kind of ice cream coney filled in three-dimensional region that we're wanting to integrate over. All right, but so to start, we need to think about what variable to move first, x, y, or z. And here, right, at least one of our equations is in the form z equals already. Let's think about moving z, and I've always done that in pink for the first variable we move, so let's stick with that. And right, the question is, do we get consistent start-stop instructions? Well, if we pick an x, y, something like that, and move in the z direction, we're going to start when we hit the waffle cone, and then move up, and then pop out of the top of the ice cream. All right, so waffle cone to ice cream over there. And what about if we pick a slightly different x, y? Well, if we move in the z direction over here, we're going to start at the waffle cone and then move up and then pop out at the top of the ice cream there. And so here we do get consistent instructions, so we're happy with moving z, and we're always starting this thing at the waffle cone and stopping it at the sphere. Right, but since these are start-stop instructions for z, we want these to have the form z equals the cone ready to go. For the sphere, though, we have to do a little bit of work. Here we have to take our sphere equation and solve it for z. And so maybe let's just do that right here. Right, we get z squared equals 2 minus x squared minus y squared. And if we take the square root of both sides, we'll get plus or minus the square root. We'll get plus or minus the square root of this stuff on the right. Right, that's telling us that yes, our sphere has a top side and a bottom side. We want the top side, and so we'll take the positive square root 2 minus x squared minus y squared. Cool. And so those are our stopping and stopping instructions for Z. Now we need to figure out the rest of the story. So to do that, right, we ask our question, what is B's shadow? In this case, it's Z shadow, right, hanging out here in the XY plane. All right, and so if we kind of take our ice cream cone and imagine, right, we have here's our little hovering flashlight that's shining down. We project this thing just straight down onto the XY plane. Right, the outer rim is going to come from right where this thing is widest, which is this place of intersection, right? So we're going to get something. Oh, so close. There we go. Right, so right there, there is our shadow in the XY plane. And now, pop quiz. What's the radius of that disk going to be? And if you said root 2, we got to be careful. We got to be careful because notice this blue disk, it doesn't stretch all the way out to the edge of the sphere, right? Which it would be a radius of root 2. It's something smaller than that. So we actually don't know right away what that radius is going to be. What we just know is visually it's got to be smaller than root 2. And we can see that on GeoGebra as well, right here. Maybe if we do maybe a side view and a top view, we come to the side, right, we can see, yes, okay, this point of intersection, it doesn't come all the way out to the edge of the sphere. So from the top view, we can see it real clearly that, yes, this inner disk, which is going to be our shadow, right, doesn't go all the way out to the edge of the sphere. It's something smaller. And so we'll need to find out what that is. But here, right, the geometry of where this disk is coming from helps us out, right? It's coming from where this cone and the sphere intersect, right? And we know how to find where surfaces intersect. All right, just for our notes' sake, let's catch up here. All right, so the B's shadow is coming from the intersection of our cone and sphere. And so, well, how do we find the intersection of these surfaces? Well, we need to substitute their equations into one another, right? And we want to do this in a way that actually eliminates a variable so that we're making things simpler for ourselves. And so here, how's that going to happen? Here, we can take our cone, try and plug it into our sphere, or our sphere, try and plug it into our cone. And I think here, the cleanest way to think about this is, well, this already has Z solved for. And so why don't we just take this and just plunk it in for Z over here in our sphere equation. All right, so if we do that, then that Z becomes the root x squared plus y squared, and that is squared, so the square root will go away. And here we have x squared plus y squared plus x squared plus y squared, and so we have 2x squared plus y squareds. And just dividing by 2, there we go. That's a nice clean equation for our, right, the outer rim of our shadow. And so right here we can see, okay, we get the unit circle, the unit circle as the shadow here in the XY plane, right? So the radius is going to be 1 for our shadow. And I wonder, just for fun, let's see if that looks legitimate here with GeoGebra from the top view. It's kind of hard to see, but I think each one of these grid lines is a distance of, I guess, a half. So yeah, there's a half and then 1. So we can kind of see that as well. All right, back to the notes. Yeah, and so again, the idea here is, hey, this is a nice circular region. Let's use polar to describe this. So we're in the XY plane, so our standard equations hold. And we can now fully set up our triple integral, right? This is the integral that we're starting with, and we found our starting and stopping instructions for z. And then these last two integrals, right, those come from our polar description of our unit circle, right? The unit circle, right, for any angle, it's going to use r's from 0 up to 1, and so r between 0 and 1, and we're going to want to do that from theta equals 0 all the way up to 2 pi in order to trace out that whole disk. So those become our limits of integration for our last two integrals. Right now our dv right, becomes dz was our rectangular, and then our rd theta for polar in the xy plane. And we're not quite fully set up yet. The reason being, right here, right behind our d's are the variables in our integral, z, r, and theta. But if we look here in our limits of integration, just the rest of our function and everything, we spot some x and y kind of, I don't know, stowaways from our original rectangular coordinates. But so into cylindrical coordinates, we want to swap these out for what they are in terms of our r and theta. And so we can do that pretty quickly, right? X squared plus y squared, that just equals r squared. And since r is positive, right, or 0, this just simplifies down nicely to z equals r for our cone. And then up here, the root 2 minus x squared minus y squared, we can actually think of this as minus right, x squared plus y squared. And we can do the same little substitution here. So this becomes a root 2 minus r squared. And so with that as our upper limit and this as our lower limit for z, this is now fully set up in terms of our cylindrical coordinates, and we can go ahead and compute this thing. If you haven't gone through and tried to compute this yet, pause the video and take a few minutes and crank through these 3 integrals, and then we'll talk about it. All right, so let's dive on in. For our first integral, we're thinking of z as our variable. And here looking at our function, this is all just a constant with respect to z. So the antiderivative is just going to be z times r. Maybe let me just, there we go. Bring the rest, a couple more steps up. So antiderivative is z times r. We're going to evaluate from our lower limit up to our top. And so if we plug in our top for z and subtract what we get when we plug in our bottom for z, here's what we get. Okay, I guess I've switched the order. I'm putting the r out front and then the root on the right, and then minus r times r. And so at this point, we now need to integrate this stuff, thinking of r as our variable. And there's actually a couple of different choices here. Right, the r squared, right, we can integrate that. But over here, this function on the left kind of calls out for a u sub. So one option is, if we wanted to, we could actually break this apart into two separate double integrals and do a u sub for the one on the left and then just work it all out. We could do it that way and it would work out just fine. Let me kind of work through this a different way where we instead just try and keep everything together and try and work through what the antiderivative of this thing is going to be, just kind of by hand with a little trial and error. Okay? And so what we can see initially, right, is what an antiderivative is going to have to look like. And so let me just write over here. Let's try and find the antiderivative for this thing on the left. It's going to have to involve a 2 minus r squared to some power. That's a squared. There we go. Right here, the power that we have originally is 1/2, right? The square root of the stuff is 2 minus r squared to the 1/2 power. Well, so where that would have to come from then, thinking in terms of antidifferentiation, is 1 higher than 1/2, or in other words, 3/2. All right, so that's the power that's going to have to be there for our antiderivative. Now, let's just try this out. If we took the derivative here with respect to r, what would we get? We'd get 3/2 2 minus r squared to the 1/2, and then times the derivative of the inside, negative 2r. And let's see what we like, I guess. So notice the 2's would cancel. And what do we like here? Well, we like the r, right? We want to see the r. But we don't like the negative, and we don't want the 3, right? We just want to have a positive r. And so what that means is let's scale those away, right? Let's include in our antiderivative the negative, and to scale away the 3, we'll need 1/3, right? And so right there, there is our antiderivative for this function on the left. And if you went through the work of u sub, that this would check out with that. This is just kind of us seeing how it can look to try and by hand construct the antiderivative with a little trial and error and adjustment. So now that we have an antiderivative for the thing on the left, we can pop that in. All right, so there's our antiderivative for the thing on the left. And then antiderivative for r squared is r cubed over 3. Evaluate that from 0 to 1. So we're going to plop in for r1, and we got to do this kind of carefully because it's a little bit involved. All right, so there's us plugging in r equals 1. All right, and so here's our first evaluation, and we're going to subtract what we get when we plug in 0. And I guess we plug it in both spots, don't we? And then here we plugged in, I plugged in 1 for r cubed as well, and we got the 1. For our second term. And so what does this become when the dust settles? Over here, 2 minus 1 is 1, and 1 to any power is just 1. So we're going to end up with 1/3 minus 1/3. And we're just going to, the two negatives are going to end up being a big plus 1/3 times 2 to the 3/2 power. And there's not too much we can do with that. Just kind of leave it like that. And then I'll scroll down the rest of the way. At this point, this thing that we're left with, right here, I've done negative 1/3 minus 1/3 is minus 2/3. This is actually just a big constant. And so to anti-differentiate with respect to theta, we just need to take that thing and multiply by theta. So evaluating from 0 to 2 pi, here's us plugging in 2 pi, and it dies when we plug in 0. And so right here, here's our nice exact form for our final answer, our value for our triple integral. And there's what it is approximately. All right, so that's how it can look to set things up with cylindrical coordinates. Again, that just means rectangular for one coordinate and polar for the others. Good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.